go ahead and go over the homework. So share screen, and any particular homework problem you want to make sure I go over? So I'll probably jump around a little bit.
From 83 to the end.
83 to the end? Okay.
I don't remember what the last one was, but that's like.
Okay, the last couple?
Yeah. Thank you.
No problem. All right, so let's see, 83 to 86. Okay. All right, well, let me know. Let's just start going over stuff. Now, this first part here was based upon making graphs. And so using transformations, you're basically flipping these around, moving them up or down. And I think there was one where you had to move it left or right because there was a horizontal translation, right? And then to determine the domain and range, well, the domain issue isn't occurring here because all of these were exponential. And so if a variable is in the exponent, that in and of itself isn't a domain issue. It would have to be the square root of x as an exponent, or maybe 1 over x as an exponent. But if it's just a variable as an exponent, then there's no problem. So all of these, the domains were all real. And the range is based upon the horizontal asymptote. So you're either below the horizontal asymptote, like number 53, or you're above the horizontal asymptote, like 52, right? So the only time the horizontal asymptote was not y equals 0 is if you added or subtracted. And so if you're subtracting, the horizontal asymptote goes down 1. So this should be y equals -1. Okay, and if you're adding, which is really what's happening here, the horizontal asymptote is going to go up 5. So this should be y equals 5. Okay, and then there was a domain dilation, which would be this right here. And so that's going to double the width, right? And so that's why that orange graph gets doubled at the very end and then moves up. So once it moves up 2, that becomes this graph. Y equals 2 is now the horizontal asymptote. Okay, and then here there was a domain dilation and a range dilation. Just whereas up here there was just a range dilation, right? So not only does it double, but it also multiplies by 3. Okay, and that's going to pull it further up and down. So these two actually are very similar to each other because if you have a half of the previous width, that's going to push it closer to the vertical, which is going to be the same effect as if you pull it up and down. So they're very similar to each other, but they're not in the exact proportion. So it's still going to look like this, and then you add 7, so the horizontal asymptote goes up 7. Okay, and then here's all the domains, and again, the only issue with the ranges, all the ranges, is just you're either above or below the horizontal asymptote. You can't equal it because, 7 minus some very extremely small number is never going to get to 7. This will never be 7 minus 0, right? So that's why you can't equal them. And then here were these equations, and a couple of them were, I thought, a little tricky. The first couple, once you rearrange them, so, with 60, once you realize that it's 3 to the 4th, that was 81, then you can just put these two exponents equals to each other, right? And the same thing with these other ones. And then here, same thing here. Don't forget a -1 exponent means the reciprocal. And then here, kind of the same thing, but you wound up with having to change the 9 here to 3 squared. So then you get your 2 times x exponent. And then when you put these exponents equal to each other, you want to use the zero product property. So notice you wind up with 3 possible solutions. 71, okay, I'll get there. Got it, Connor. Let me let Sam in. Okay, so he'll be getting here shortly. All right, so where were we? So yeah, so then most of these is kind of the same thing. Now, once you get to 67, now you're going to have to start converting both. So here you had to convert the 8 to 2 cubed and the 16 to 2 to the 4th. And then you have your multiplication because now you got powers outside parentheses. And then that winds up being this equation. Same thing here, converting both the 9 and the 27. Same thing here, but you only have to convert the 27 here. And then don't forget your powers outside parentheses. So that's why that's 6x equal to the other exponent. Okay, and then the same thing here, right? Okay, and then we get to the rest of them. Now, the rest of them are a little more involved, starting with 71. So you got 4, 2, and 16. So the smallest number to use for a common base would be 2. Okay, and then once you do that, well, you're multiplying common bases, so you add the exponent. So the 2x adds to the x squared to get your combined exponent. So remember, if you multiply common bases, you can add the exponents, and so that's this next step. And then once you get to that step, now you just put these two equal to each other. And the same thing with 72. You want to convert both of these to base 3. And then once you get down to the second step, you got common bases. You're multiplying common bases. You add the exponents. So this 4x is going to add to that 3x squared. And then now you can put the exponents equal to each other. And then 73 and 74 are probably straightforward, but let me let 2 of the students in. And wait till that happens. And then 75 and 76 were similar to each other. You had that e here, and so you want to rearrange that. So that's why I put a -2 exponent. And now just like over here, when you had common bases that were multiplied, you have e's that are multiplied. If you multiply common bases, you add the exponents. So that's why this becomes 3x minus 2, and then you just solve that equation. And the same thing here, right? Once you go ahead and multiply the common bases, you can add the exponents. And so that's the next step here. And then you can just put the two exponents equal to each other. Okay, and then here, this was just a matter of rearranging these equations. Let me see. And so with this one, right, you can just replace the x with -1, and then it's just a matter of solving that problem, right? And then putting that equal to 122, you add 3, and then, oh, look, 125 is the same as 5 to the 3rd power. So you could do that with these. These you wound up with something that you could do just using number sense, but there are times when we're not going to be able to do this. Instead of 125, this might be 119. Well, we can't use number sense, right? We can't raise 5 to a number off the top of our head and get 119. So that's when we're going to start using what are called logarithms. But you didn't have these issues with any of these. Okay, now 83. Now what we want to do is we want to use what they gave us in the problem that we're going to use substitution. Okay, so I replaced the 4x that was over here because -2 times x, that's the same thing. And that's 7. And so we just do 7 to the -2 power. Okay, the same thing here. We want to replace the 2x in the problem and put it equal to 3. So we got to figure out how can we make this become 2x? Well, you can separate it that way. And then once you change the 4 to 2 squared, you can go ahead and rearrange these exponents because it's still going to be -2x. But this just gives you a way to visually see, oh, we're going to substitute 3 there. And so then that's how we do that. Same thing here. This is what we're given. So we need to find some way to get a 3 to the negative x so we can replace it with a 2. So this is what we're given. Okay, well, I rearranged it this way because that's still going to be positive 2x when we multiply. And now we have a way to substitute the 2, and so then that becomes 1/4.
Mr. Napoli, can you let Zach into the call?
Thank you. I just caught it. Yeah.
Okay, great.
Right on. Yeah, we're helping each other out, right?
Yeah.
Okay. So, yeah, I get so caught up in what I'm doing. Just love explaining math. So here we got for 86, this is defined as 3. All right, so what we want to do is create a 5 to the negative x so we can replace it with a 3. So this is what we're given. All right, so I just changed it. And so this is still 3x when you multiply. But now we can see how to substitute and put a 3. So we put the 3 there, and then we can solve the equation. Okay? All right, well, today we're going to start looking at logarithms a little bit. And the thing is when we look at numbers, we can scale numbers in any kind of way we want. So there's a number of different ways of scaling things. We can use a linear scale, right? Well, if we used exponents and we scale based upon the exponents, right, that's going to depend upon the base. So if we're going to use a base 1, these are always going to be 1, right? If we use the linear scale, right, then this would become negative 24, negative 12, 0, 12, 24, 36. If we use an exponential scale, then this will become the reciprocal of 2 squared. This will become the reciprocal of 2. This will become 1, because anything to the 0 power is 1. 2 to the first, 2 to the second, 2 to the third. Now notice that the middle is not 0 with exponential, whereas with a linear square it is. All right, and so this basically means as we go into the future to the right, we're doubling the previous numbers, whereas in the past, if we go back into the past, we're having half as much as we get later. Right? We could do this with other values too. Right? Now, I'm just going to assume you know what I'm doing. So 1 over 3 squared, reciprocal of 3, 1, 3, 9, 27. Same thing here. If we're going to go ahead and create a scale based upon an exponential model with base 5. So 1 over 5 squared, right? Reciprocal of 5, 1, 5, 25, 125. When we refer to values based upon exponents, we call those logarithms. Okay, and the relationship between logarithms is we get the exponent we need to represent a value, but it depends upon the base. So let's say we wanted to represent the value of 5. All right, so we want to represent the value of 5. Well, if we're using base 5, the exponent would be 1. Right, so the log using base 5 to get a value of 5 would require an exponent of 1. That's what that means. This value of 5, when the base is 5, needs an exponent of 1. That's what that statement means. But what if we were using a different base? What if we were using base 3? Okay, well, if we're using base 3, then the log using base 3 of 5 is not 1. Because look where that is. That would be in between 3 and 9. So if we want to get an exponent using base 3, we're going to have to use an exponent between 1 and 2. And it's not intuitive, but we know whatever that exponent is, it's in between 1 and 2. Okay, so logarithms are scaling values using exponents, but the scale is completely dependent upon the base. And we can do this with e too. Now e is not intuitive. You know, e would be 2.71 blah blah, right? And if we did that with this one, I calculated this earlier, this would be 0.135, this would be 0.367, this would still be 1, this would be 7.38, and this would be 20.08. So if we wanted to represent the logarithm using base 5 of the value 5, we got an exponent of 1. If we wanted to use the logarithm using base 3 to represent the value 5, we needed an exponent between 1 and 2. But with e, that's the same as well, because e is pretty close to 3, 2.71. So we would still need an exponent in between 1 and 2. Okay, so the logarithm using base e to get a value 5 is in between 1 and 2. Okay, now the thing is, some logarithms are pretty common. And the relationship between logarithms and exponential is that they're the reverse of each other, right? So if we wanted to represent this original problem that we had right here, when we used this base that was the same as the value, we needed an exponent of 1. Well, if we went ahead and took that base and applied the exponent of 1, we would get 5. And so the output of the logarithm is the same as the input of the exponential function. So these are inverses of each other. Okay, and so the notes for that, let me click right here. That's what this means. Let me zoom that down a little bit. Okay, so a logarithmic function is going to get you the exponent that you need to represent a certain value depending on the base. And so you get the exponent as the output of the logarithmic function. And if you apply that exponent to base, you get the value. So these two are inverses of each other, and you can switch them around. Okay, anybody want to ask any questions about that? So we're going to do 2 or 3 things of how we use this in applications. We're not going to get to the graphs of logarithms today. That's going to be in the future. And while you guys are here, this is kind of my layout of how I think we'll go. Now, seniors, your last day is Thursday, May 14th. All right, that's your last day. And so as far as your grade goes, you'll have the same grade at the very least that you got at the progress report. So you can't do any worse than that, guaranteed. So anything you do here, you know, I'll mix together and we'll determine what the final is. But all right, just thought I'd share that with y'all while I'm thinking about stuff. Okay, so let's go ahead and use this to rearrange from a logarithmic expression to an exponential expression, because that's one way we can use this to solve problems. Okay, so, you know, for instance, if we had 64 equal to some base to the third problem, well, maybe we know this. right? Maybe we already know, oh, okay, that's probably 4. Well, let's go ahead and rearrange this to the logarithmic. We don't know what the base is. The value is 64, and the exponent is 3. Okay, so the log of the base that we don't know of 64 equals 3. So that's how you could rearrange it. Now to solve this, just raise both sides to the 1/3 power if you just want to solve this. All right. Now let's say we had e to the 3rd power equals x. Okay, well, we can solve that. We just get our calculator, raise e to the 3rd power, no problem. But what if we wanted to rearrange this to the logarithmic equation? Okay, well, this would be the value, because that's what we got when we raised the base to the 3rd power. That's the exponent, and that's our base. Okay, so the log using base e of this value required an exponent of 3. So the log expression always equals the exponent. So as soon as you see the exponent, that's what the log expression is going to equal. And whatever the base is, it's going to be whatever you're applying the exponent to. Now, a lot of times we use e so frequently that we don't really write it like this. We use a special notation. So Heman's abbreviated, instead of writing 4 letters, we just write 2, because we use this quite often. In fact, I was using the exponential model when I was gathering, and still am, all the statistics from COVID cases. So I'll share that with y'all towards the end. I'll share how I did that, what I was doing. All right. And so this is really what we use right here. Now, another common one is 10. So let's say we had something like that. Okay, well, we could maybe solve this. It's a little tricky because we don't know the exponent, whereas at least here we could use the reciprocal exponent. And here we could just apply the exponent to the base. But what do we do here? What? It's not 9, because that would mean 9 zeros. We got 2 zeros, right? If it was 3 zeros, then it would be 3, if this was 1,000. So we're somewhere a little less than 3. But how the heck are we going to guess that? We can't. This is where the logarithmic expression is helpful. If we rearrange this, well, we know this is the value. The exponent is unknown, the x, and this would be the base. Okay, so the log using base 10 of the value of 900 equals what we want, the exponent. All right, so just do that. Now, another common exponent, base is 10. So this also happens quite frequently. So people don't even bother to write the 10, right? So if you don't see a number there, it's base 10. We call these common logarithms. Okay, whereas this is called a natural logarithm. Okay, the reason it's ln is because it's a Latin word, right? And in Latin and Romance languages like French, Spanish, Italian, Portuguese, the adjective follows the noun. So in English, the adjective precedes the noun, natural logarithm. In Romance languages in Latin, it's logarithme natural. So instead of saying red hat, they say hat red. And so that's why it's ln. By the way, y'all know what they call these logarithms? Anybody know? Because logs got rhythm. All right, y'all. So Now we're going to look at determining the domain. Okay, and then I might show y'all how to rearrange some more of these. The domain of these. Okay, well, we got to think of what that means. Okay, if we have something like this, right? Remember, the domain can be any real number. There's no issues with exponents in general. You would have to have some other operation that causes a problem. So now we got a domain issue because we added an extra operation in the exponent, whereas now we don't. Okay, and remember, that's why these graphs do this. So forever to the right or forever to the left. Right? So this would be multiplying by 10, we go to the right. This would be dividing by 10, we go to the left. So notice this will never equal 0. Because 10 to any negative exponent means 1 over 10 to a big positive exponent, and 1 over any number is never going to equal 0. So the domain here, the x's are all real numbers, but the range, the y's have to be greater than 0. Now remember the inverse? So if we switch this to the inverse, the log of y equals x. Now I'm not switching the variables just to make a point, but if we use function notation, then we would want to switch the x and make this the inverse notation symbol. All right, so now notice, well, the domain has to be greater than 0. And the range can be any real number. Okay, so this is the domain issue. Whatever value we want to relate to an exponent has to be a positive number. We can't just apply an exponent to get a negative number. So that's the domain issue. Has to be greater than 0. All right, so if we had this function, then the domain would be solving that problem. So the domain would have to be greater than that. Because once this gets to 0, that means we're getting an exponent to get a value of 0. There's no way. There's no number you can apply an exponent to get 0. That doesn't cause 0, that's 1. And remember the scale, as we went to the right, we went bigger than 1. And as we went to the left, we started to go less than 1, but greater than 0. Remember the scale in the beginning? Okay, that's why I do that. So it's, a little easier to understand when you have some number sense behind it, I think. All right, let's do one more of these, and then we'll look at rearranging to get the inverse. Let's see. Okay, we're good for time. Cool. Yes, I was worried about that. That's why I gave you a small warm-up today. All right, so let's say we have this function. Okay, now it goes without saying, but stop me at any time you get confused, okay? Now this is a little more demanding because we got two issues here. We got the domain issue internal to the logarithmic function, and this is the natural logarithm. So this is going to based on e. And we also got the external operation. So we got two parts to this domain. The first part, the domain of the inner function, that's got to be greater than 0. And then the domain of the external operation, we have to take square roots greater than 0. So then this is the second part of the problem. Okay, well, this first part, we can do that. The second part's a little tricky. Okay, this is where we're going to have to rearrange the exponential. And we got inequality. All right, so subtract 1. Okay, so the exponents are bigger than -1. That's just remember, you can think of a logarithm as an exponent. So these are the exponents to base e. So the exponents are going to be bigger to -1. Okay, so again, that's the exponent, that's the value, and the base is e. Okay, so the exponents are bigger than -1. So e to the negative 1, it's got to be greater oh, wait, no, sorry, my bad. So the value's got to be greater than that, my bad, almost missed it. My point is saying the exponents has got to be greater than 1. So this value has got to be bigger than the base to the negative 1, because this means the exponent's got to be greater than negative 1. So the value's got to be bigger than the base to the negative 1. So this value we're going to get by using bigger exponents than negative 1 to e. That's a little tricky, but notice that we're open on the x minus 3. So we should still be open on the x minus 3. Okay, so now we can finish this one. So greater than e to the negative 1 plus 3. Okay, now when you look at these two, which one is more inclusive? Well, these are practically both the same, except of this little tiny thing. So this is a little bit bigger than 3. So we'll pick this one because that's more inclusive. If x is greater than this, it's also greater than 3. So the two issues are moot. If we pick this one, however, then there's going to be a little bit of value between 3 and this that'll fail the outer operation. All right, so the complete domain would be that. Okay? Everybody good with that? Okay, so let's look at rearranging things. So let's say we had this. All right, so this is why we did those inverses a couple days, because we're going to have to be able to do that here, right? Okay, so what we're going to do is we're going to put this equal to y, all right? And we're going to go ahead and solve this for the log and then switch it to the exponential. So subtract 5, divide by negative 2. Right? Now you could also, instead of making it negative 2 on the bottom, you could just put the negative on top. I like myself to get into the habit of not having a negative denominator. It just makes things a little less demanding, I think, in the long run. Okay, so now we got our log equal to an expression. So this is the exponent. The value is x minus 5, and the base is 2. All right? So we got the 2 raised to the exponent equaling the value. And then just add 5. Now I'm going to go ahead and switch it to the function notation. All right? Whereas this would have been the original function. Okay, so once you get the logarithmic expression equal to the other side, then you can switch this to the base exponent value. So this log equals the exponent, so that's the expression for the exponent. Our base with 2, so 2 is going to be raised to that exponent expression, and that's going to equal the value, so that equals to x minus 5. So whatever's in the log is what the base expression is going to equal. And then I just added 5, and then I just switched this to the x so that we can use the inverse notation.
So this is the inverse of that log. That's
Exactly.
what this is. Okay.
This is the inverse function on the bottom of the original function. And then I erased and put a y there, but that was originally the function notation. Is everybody okay with that? Okay, so y'all are going to have the quiz on Thursday, and I'll just verbally tell you It's going to be inverses with range and domain. And then, oh, I have my paper over there. Let me get my paper so that I don't miss anything, okay? Oh, yeah, here's I misplaced it. Well, okay. So then we had the compound and simple interest, okay? And then we started to get into making graphs of the exponential stuff. And I probably won't throw this on there. So this is probably not going to be on there, right? And then we also had the composite functions, right? And then the domain of the complete result. And that's, yeah, that's fair. That's it. I'm not missing anything. I'm just double checking in my mind real quick. Yeah. Okay.
Are you gonna put that list on Google?
Yeah, I will.
Drive?
I am. I will. I'll post it on there.
Thank you.
That's just that's probably we're looking right in my face. I wish I put it. I put it up here. Where?
It happened.
Yeah, it does. Anyway, I mean, if worse comes to worse, I just make a new one. No big deal. All right, we good? Okay, I'm gonna go ahead and jet.